Welcome everyone to the One World Combinatorics on Words seminar. Our speaker today is John Campbell, who's at Dalhousie University, and he is going to speak to us about the evaluation of infinite products involving automatic sequences.
Okay, so I just want to begin by thanking the organizers of this seminar and by expressing that I'm very grateful to have been invited to give a presentation on my research. And on a personal note, I just want to express that the research due to Jeffrey Shallot on automatic sequences has been of interest to me for many years, and that it is an honor for me to be giving a presentation on a published paper of mine that is very much inspired by Dr. Shallot's research. Okay, so I want to proceed by going over some introductory material concerning how automatic sequences relate to the evaluation of infinite products. In this regard, a notable research contribution concerning automatic sequences and infinite products is due to Jeffrey Shallot, and introduced a conjectural recursion for defining the 2A Morse sequence in terms of the partial products associated with an infinite product that admits a closed form evaluation. Now, the famous 2A Morse sequence may be seen as being almost prototypical as an automatic sequence, and since the sequence can be defined in a natural way in terms of its relationship to an infinite product evaluation, this illustrates how automatic sequences are so intimately associated with infinite products. Shallot's conjectured product identity for the 2A Morse sequence was subsequently proved by Jean-Paul Alouche and Henri Cohen, and I have indicated two standard ways of defining the 2A Morse sequence following the product construction conjectured by Shallot and proved by Alouche and Cohen. So I am adopting the convention whereby a given entry of the 2A Morse sequence may be defined as the number of binary digits modulo 2 equal to 1 in the base 2 expansion of the index of the aforementioned entry. And I have provided a deterministic finite automaton that may be used to provide an equivalent definition for the 2A Morse sequence. If we consider the definition for the 2A Morse sequence in terms of binary expansions, this naturally gives rise to a recursive definition for the same sequence if we consider the parity of a given index for an entry of the 2A Morse sequence. And this can be used to, in a sense, translate the recursive structure associated with the 2A Morse sequence using an infinite product. And this can be formalized with the proof of Jeffrey Shallot's conjecture. So I just want to briefly illustrate the product-based recursion I have indicated for the 2A Morse sequence. So starting from the base case with U indexed by 0 equal to 0, when we take the product given previously uh, and restrict it to the case whereby the index j equals 0, we obtain the value 0.5, which is strictly less than the target value of 1 over the square root of 2. So according to the recursive procedure for the sequence denoted as u, we set u indexed by 1 to be equal to 1, and we continue in the manner I have illustrated. So for the following value of 2 over 3, this is again strictly less than the target value. So you can see how the 2A Morse sequence starts to emerge from the products we have computed so far if we consider the initial entries for the sequence denoted with U. So as illustrated, these initial entries are equal to 0 and 1 and 1 and 0, and these values agree with the initial 4 entries of the 2A Morse sequence. So Shallot's conjecture was proved in this 1985 article by Alouche and Cohen that was published in the Bulletin of the London Mathematical Society. And I just want to go over some relevant background material that is based on this article and that concerns infinite products and automatic sequences. Okay, so the techniques due to Alouche and Cohen in this 1985 article are very much based on the manipulation of Dirichlet series. So I just want to go over some preliminary notation concerning the Dirichlet series involved in the work of Alouche and Cohen. So as I have indicated, we are going to be fixing an integer denoted as q, and we are going to be fixing a root of unity, and we are going to enforce the condition that the degree of this root of unity divides the integer q. And I am adopting the notation from Alouche and Cohen, giving the summation of the digits of a given non-negative integer in the expansion in the base denoted with q. We are going to be making use of the specified Dirichlet series defined in terms of the sum of digits function I have indicated. And as something of a first step toward obtaining infinite product identities from these Dirichlet series, we are going to determine the analytic continuation for the analytic continuations for the functions defined in terms of these Dirichlet series. So we begin by we begin by applying a series multisection in the manner I have indicated. This series multisection is given by the residue classes modulo q, and we are applying this multisection in order to apply a recursive property of the function defined by Alouche and Cohen, given by sums of digits in base q. So after making use of this recursion, as I have indicated, we manipulate the resultant summand in order to apply the generalized binomial theorem so as to produce the triple summation shown in the current slide. Now, we are permitted to apply an interchange of limiting operations since the summations under consideration are absolutely convergent for arguments with a real part strictly greater than 1. So by reversing the order of summation, this gives us a way of expressing this function f as an infinite summation in terms of the same function. So you may recall that we are letting zeta denote a root of unity that is not equal to 1. And our choice of the value for zeta gives us the vanishing for the specified summation of powers of zeta. And this leads us to apply a reindexing argument to express the first of the Dirichlet series given by Alouche and Cohen. So previously, we obtained convergence under the assumption that the real part of the argument for our Dirichlet series is strictly greater than 1. However, the formula we have obtained for expanding the function f as a series involving f and positive indices allows us to extend the original definition for f so as to admit arguments from the whole complex plane. Now, you may be wondering how this analytic continuation could be useful in terms of the evaluation of infinite products involving automatic sequences. And in this regard, if we were to take the derivative at 0, then our analytic continuation allows us to obtain an explicit evaluation in closed form. And the application of term by term differentiation results in logarithmic expressions within the summand. And this gives us, in an equivalent way, a closed form identity for an infinite product involving the sum of digits function defined by Alouche and Cohen. The closed form evaluation for f prime at zero may be derived using a relation between the two Dirichlet series defined by Alouche and Cohen, and this in turn may be derived using the analytic continuations for the same Dirichlet series. So according to the convergence of the series given by the analytic continuation of the first Dirichlet series, we are permitted to apply an interchange of limiting operations given by dividing by the argument and then taking the limit to zero within the summand. This has the effect of producing a logarithmic expression within the summand in the manner I have indicated. And this gives us a way of expressing the derivative of f at zero as the natural logarithm of an infinite product. In particular, this gives us a way, as Alouche and Cohen have demonstrated, of evaluating the infinite product corresponding to Jeffrey Shallot's conjecture concerning the two-way Morse sequence. So through the application of the interchange of limiting operations I was referring to, together with the closed form evaluation of the derivative at zero of the analytic continuation of the first Dirichlet series we have defined, this gives us a remarkable infinite product identity given in an equivalent form, as in the theorem due to Alouche and Cohen I have indicated. I have also provided a screenshot showing a numerical verification of this theorem with the use of the Wolfram Mathematica computer algebra system. So you may recall that we are letting zeta denote a root of unity such that the degree of this root of unity divides the base denoted as q. And you can see how I have obtained a high precision numerical estimate of Alouche and Cohen's series using the Wolfram system. So this theorem on the current slide is quite remarkable due to how it provides an infinite family of generalizations of what is referred to as the Woods-Robbins product, which may be seen as one of the most basic infinite products that involves an automatic sequence and that admits a closed form evaluation. So I just want to go off on something of a tangent, or to go off in something of a different direction relative to the subject matter we have been going over. And I want to describe a new research area or research topic that I started to consider while preparing for my presentation. So as I was using the Wolfram programming language to numerically verify the main results given in the research article by Jean-Paul Alouche and Henri Cohen, to which I have been referring, I started to consider experimenting with variations and generalizations based on the analytic techniques concerning Dirichlet series involved in the aforementioned article. And this led me to discover new infinite product evaluations that I would consider to be reminiscent of identities discovered by Bill Gosper, who is one of my mathematical heroes and one of my personal heroes. Bill Gosper is a very major figure in the history of computer algebra. So just a few days ago, I sent an email message to Jean-Paul Alouche concerning my discovery given by the first out of the two product formulas shown on the current slide. And Dr. Alouche sent me a very inspiring response that suggests to me an extent of research potential based on the techniques underlying this discovery of mine. And I just want to briefly describe these techniques. So If you would recall the theorem provided by Alouche and Cohen I had indicated, then you may recall this theorem provides an explicit evaluation for an infinite summation involving a root of unity raised to the power of the sum of digits function defined previously. And the corresponding summand involves a logarithmic expression as a factor. So you may recall that the restriction on the expression denoted as zeta was required in the derivation of the analytic continuation for the first Dirichlet series defined by Alouche and Cohen, with zeta as a root of unity such that the degree divides the base denoted as q. But based on my implementation using the Mathematica system to numerically verify the evaluation given in the aforementioned theorem, it seems that this theorem holds true more generally for complex values of zeta apart from roots of unity. Now, I have not yet proved this experimentally discovered generalization, but for the time being, if we accept that this conjectured generalization is valid for real values zeta or complex values zeta that are suitably bounded, then we can consider how to alter or manipulate the corresponding summand by applying integral or differential operators if possible with respect to the real or complex variable zeta. And this closely relates to the subject matter involved in my recent publication concerning the automatic sequence known as the period doubling sequence. So by applying term by term integration, this led me to experimentally discover the first out of these two product evaluations given in the current slide. So if you would consider the resemblance between the two product evaluations I have provided, you will find that these evaluations are both given by a power of 2 with an expression involving the constant pi in the exponent. And based on my research experience and research background concerning infinite products and infinite series, I would consider the displayed evaluations to be of a very unusual nature. And I have not been able to find any other product expressions for a rational number raised to a power involving pi. And in this regard, the first product formula being displayed is especially notable in the sense that it provides expansions for partial products. So we obtain algebraic expansions for the partial products associated with the infinite product. So I have been focusing in this presentation so far on background material related to a recently published research paper of mine, and I want to start to move toward discussing the material in this recent paper of mine, which concerns infinite products involving the period doubling sequence, the period doubling sequence. And I want to give something of an outline based on the evaluation method involved in my paper and to describe how this evaluation method relates to the material in the article by Alouche and Cohen I have been reviewing. So the techniques applied in Alouche and Cohen's paper very much relied on Dirichlet series defined through the sum of digits function I defined earlier. And you may recall how there were a variety of series manipulations and series rearrangements that were required in order to obtain the analytic continuation. From this analytic continuation, an explicit evaluation was derived for f prime at 0 for the Dirichlet series denoted with f defined earlier. So through the application of term by term differentiation together with the evaluation for f prime at 0, this provides, in an equivalent way, a family of closed forms for infinite products involving roots of unity raised to the power of the sum of digits function. In my research article concerning the period doubling sequence, a different but related approach was applied to evaluate infinite products. So instead of using Dirichlet series or analytic continuations, my evaluation method relies on the application of integral operators to the term-by-term expansions for series that are equivalent to infinite products that can be reduced using recursive properties of an automatic sequence to an elementary function. I was previously referring to how we can, in a sense, translate the recursive definition for the two-way Morse sequence into a corresponding infinite product identity. And informally, this kind of translation can be applied much more broadly using automatic sequences. And this led me to explore how properties of the period doubling sequence can be thought of as being encoded in infinite product identities. It seems that integral operators have not previously been applied in relation to the study of infinite products involving automatic sequences, and this led me to pursue an interdisciplinary research project drawing upon my experience studying automatic sequences at the University of Waterloo under the supervision of Jason Bell, and drawing upon my research background in the field of special functions theory. And with my PhD thesis, having involved the use of integration techniques related to my research article concerning the period doubling sequence. So one of the main sources of inspiration for me in relation to my discoveries concerning the period doubling sequence is given by an article in the Ramanujan journal by Alush, Riazat, and Shalit that introduced evaluations for infinite products that are closely related to my discoveries involving the period doubling sequence. So I just want to go over some background material concerning this contribution to the Ramanujan journal. In this regard, one of the most basic and well-known results concerning infinite products involving automatic sequences is referred to as the Woods-Robbins product identity, and was generalized by Alush and Riazat and Shalit in this Ramanujan journal article. And there is a rich history surrounding this Woods-Robbins identity with regard to the extensive literature on infinite products closely associated with this Woods-Robbins product evaluation, which has been generalized in many ways, including with the Dirichlet series-based techniques we were discussing earlier. The recursive techniques given by Alush, Riazad, and Shalit were applied to obtain evaluations for infinite products given by altering the rational function involved in the Woods-Robbins product and by altering the exponent of this rational function. And this inspired me to explore how a similar kind of approach could be used with the period doubling sequence and with the use of integral operators in the manner I was describing earlier. So following the work of Alush and Riazat and Shalit, we define the bivariate function f in the manner I have indicated to generalize the Woods-Robbins product, and we define this univariate function g in relation to f as I have specified. And there is a remarkable recursion for the f function that was introduced and proved in the Ramanujan journal reference I have cited. And this recursion is given by how we can express the function f with arbitrary arguments given by complex numbers that are not negative integers as a quotient of the function g. And the authors of the reference I have indicated used a bisection applied to the infinite product corresponding to the function f and then manipulated this bisection according to the recursion satisfied by the two-way Morse sequence. And this inspired me to investigate how the recursivity associated with the period doubling sequence could lead to new results of a similar nature. Okay, so I have been referring to my research on the period doubling sequence, and I want to emphasize that the period doubling sequence may be seen as an important instance of an automatic sequence. And this motivates the pursuit of new research endeavors and new research directions that have to do with number theoretic properties or combinatorial properties associated with the period doubling sequence. This points toward an interdisciplinarity that led me towards something of a combination of automata theory and special functions theory in terms of the principles underlying my discoveries on the period doubling sequence. The interdisciplinary interest in the period doubling sequence is reflected in the many different ways of equivalently defining the sequence, as these equivalent definitions point toward applications within number theory, automata theory, and the field of combinatorics on words. So in this regard, you can see how we can define the period doubling sequence in terms of a divisibility property, in terms of a deterministic finite automaton, and in terms of a homomorphism defined on the free monoid over a binary alphabet. So with regard to the subject matter of my recent publication on the period doubling sequence, I want to proceed by highlighting a motivating result or a motivating example given by a new evaluation involving the period doubling sequence. And you can see that this evaluation is given as a combination of fundamental mathematical constants, including pi and e and Catalan's constant. And you may find that the corresponding infinite product bears something of a resemblance to the products involving automatic sequences given previously in this presentation, in the sense that this product is given by taking an elementary function and raising it to the power of an entry in an automatic sequence, and by taking products of consecutive or successive expressions of this form. However, there is a noticeable difference with this new product, since this new product does not involve a rational function raised to powers given by entries in an automatic sequence. Instead, we have an elementary function that is not a rational function and that is again raised to powers formed from the entries of an automatic sequence. It seems that infinite products of this latter form had not previously been considered in the relevant literature, at least to my knowledge or to any significant extent. The relevant literature on infinite products and automatic sequences. So this motivates the integration-based arguments I have introduced and applied to prove the motivating result under consideration and many further results of a similar nature. So I want to clarify how the recursivity of the period doubling sequence can, in a sense, be thought of as being encoded through the use of infinite products. So if we again consider the equivalent definitions that I had provided for the period doubling sequence, this leads to the recursion that I have indicated. So the first definition gives us that b indexed by n is equal to the highest power of 2 dividing n plus 1 modulo 2. And you can see again how this leads to this recursive definition I have given. And this comes from taking the residue classes modulo 4 of the indices for the period doubling sequence. So how can we make sense of the idea of translating this recursion through the application of an infinite product? By taking a convergent infinite product and by having this infinite product or by having this infinite product involve a function raised to the power of d indexed by n, by applying bisections according to the congruence classes modulo 4, and by simplifying the resultant products according to the recursion for the period doubling sequence, this leads us to rearrange the simplified products so as to obtain a single product involving b indexed by n in the exponent in the manner I have indicated. This bisection-based and recursive approach is closely related to the previously cited work by Alouche and Riazat and Shalit, and this motivates how we can build upon this past work with the use of new and integration-based arguments. So I just want to spend the remainder of the presentation going into some more detail regarding this publication of mine on the period doubling sequence, and I also want to discuss some potential follow-up projects or future areas of research. So let's once again consider this identity that that I had given on the previous slide. So we can think of this first identity shown on the current slide as capturing or encoding recursive properties of the period doubling sequence. So the core idea or one of the core ideas of my paper or underlying my paper on the period doubling sequence has to do with how we can reduce the right hand side of this identity to an elementary function so that we could then manipulate this equality for the special case whereby the right hand side is an elementary function, so that we could then manipulate this equality in an equivalent infinite series form using integral operators. So how could we get an elementary function for the right hand side for this identity? Well, it was known to Euler that convergent infinite products of rational functions admit evaluations in terms of the gamma function. So this naturally leads us to apply the reflection formula for the gamma function. So by letting this function R be a rational function with free parameters subject to appropriate restrictions, and under the assumption that all of the products we are working with are convergent, by systematically searching through different combinations of these free parameters in the hope of obtaining an elementary function in the manner that I've indicated. Well, this leads us to take the natural logarithm of both sides of the resultant equality in the manner I have indicated. And this inspired me to experiment with manipulating this infinite series shown at the bottom of the screen here. So I just want to clarify what I was just describing. So why don't we take a very general what can be thought of as a very general rational function that admits the desired convergence requirement that I was referring to. So with the free parameters that I've indicated subject to the given restrictions, I used the Mathematica system to search for combinations of rational values for these parameters so that we would obtain a reduction to an elementary function in the manner I was describing earlier, again, according to the reflection formula. So I have provided an explicit evaluation in terms of the gamma function for the right-hand side of this identity involving the period doubling sequence. So why don't I just provide you with a concrete illustration as to this process I was describing. So for this first lemma, you see what I mean. We obtain reduction to this very nice and simple elementary function, and we can think of taking this lemma a step forward by once again taking the natural logarithm of both sides and then applying summation techniques or term by term operators to, in a sense, go above and beyond this elementary evaluation. So just to illustrate a closed form that we would obtain from this lemma, an illustration of this lemma providing a closed form evaluation is given at the bottom of the screen here. So the first theorem in the paper of mine I've been referring to is given as follows, and this is of a very similar flavor relative to the motivating example I was describing. And by once again taking the natural logarithm of both sides of the identity involving the elementary evaluation, by once again taking the natural logarithm of both sides, we obtain this infinite series identity. But now we're going to have to deal with special functions when we start to consider the anti-derivatives that we would obtain from this evaluation technique that I've been describing. So I haven't defined this special function shown toward the bottom right of the screen. This Li indexed by 2 function denotes the dilogarithm function. And you can think of this as accounting for where Catalan's constant comes from in terms of the evaluation in this theorem. So I just want to further illustrate this phenomenon with a very similar lemma relative to the lemma given previously. So again, we obtain this elementary evaluation through the reflection identity, the reflection formula for the gamma function. We once again take the natural logarithm of both sides, and through term by term integration, this results in the same special function as before, this dilogarithm function. So I may be kind of running out of time here, so I just want to explain that we can go even further. We can go beyond the dilogarithm function to the trilogarithm function. We can experiment with all kinds of integral operators and combinations of operators. It's a very interesting area. So I just want to remind you of this famous and beautiful mathematical constant, Apéry's constant. We obtain this very intriguing combination of fundamental constants through tweaking the process I was describing before by using a variation of the procedure I was describing previously. So you can see in this case, we obtain this combination of Catalan's constant and pi, and Apéry's constant and pi squared, and the fourth root of 2 and e. So in this case, the integral operator that we would use, it's somewhat difficult to explain, but it's given explicitly. We take a parameter multiple of the integral operator instead of just applying term by term integration. And I have provided here an evaluation of a very similar flavor, of a very similar nature as before. And I also want to emphasize that there are all kinds of emergent connections with different kinds of special functions. So through my research based on this product evaluation method I've been describing, I've come to discover how there's a close association with the special functions known as log sine integrals and the Clausen function. And this is very nicely related to the research of the Borwein brothers in the field of experimental mathematics. So just to start wrapping things up, I just want to go over I just want to briefly describe some follow-up or potentially future areas of research based on the topics that I've been discussing. So I have been experimenting with and considering some new research directions based on the use of what may be referred to as Abel type summation lemmas. So if we think of what is referred to as the Abel lemma on summation by parts, or the modified Abel lemma on summation by parts, we can think of how this can be translated, or how this could be applicable using infinite products. Uh, it's somewhat difficult to explain, but I can see direct applications. So we could consider how the techniques we've been going over, how these techniques could be much more broadly applicable using automatic sequences, or say infinite families of automatic sequences satisfying certain conditions, instead of the specific cases I have been using the specific cases given by the 2A sequence and the period doubling sequence. I'm also very interested in further developing techniques for evaluating products of this form for non-rational functions f of n. And this leads me to go over some topics given in a paper that I recently submitted for publication. So if we think back to this topic, if we think back to what I was describing about how there isn't very much known about the evaluation of infinite products given by a non-rational function raised to the power of an automatic sequence, this led me to consider some different kinds of ways of approaching this kind of problem. So it's somewhat difficult to explain, but if you think of how I kept on emphasizing how we obtain, how we would want or hope to obtain a reduction to an elementary function on the right-hand side of this identity, well, instead of restricting ourselves to elementary functions, maybe we could mimic my technique using special functions, and this led me to investigate the use of these remarkable integral formulas due to Gosper. So you can kind of see what I mean. If we obtain a reduction on the right-hand side to an expression involving the gamma function, well, by taking the natural logarithm of both sides, we could come to new applications of Gosper's work on these log gamma integrals. And I've provided an illustration here. I've provided an example of the kind of formula that we would obtain involving what is referred to as the Glaisher-Kinkelin constant. And I just want to conclude my presentation by briefly describing one more area of research related to what I've been discussing. So you may recall the anti-derivative evaluations that I provided in terms of this logarithm function. well, I'm very interested in areas in special functions theory concerning this dilogarithm function. For example, the construction of what are referred to as dilogarithm ladders, and how we can obtain closed forms from linear combinations of dilogarithms more generally. Well, this motivates how we could use automatic sequences in a similar way with relative to how we obtained dilogarithm evaluations previously, if we were to instead make use of closed forms for this Legendre pi function or the inverse tangent integral or the Clausen function. These are very closely related to the dilogarithm function, and this seems to be a promising area of research to pursue. So this concludes my presentation.
Thanks very much. Questions? I see Hajime has a question. Go ahead, please.
Could I see page 21st? I'm sorry if I missed your talk about is there a closed formula including zeta 5? This is related to zeta 3.
So could we obtain a similar evaluation involving zeta 5 as opposed to zeta 3?
Yes.
Yes, it's somewhat difficult to explain, but it makes sense intuitively. If we use a similar kind of operator, I think it would be possible to obtain to obtain higher values, to obtain the Riemann zeta function with higher arguments. So if you consider the integral operator toward the bottom left of the screen here, I can see in my mind how this would work out. It's difficult to explain, but I think just by tweaking, just by altering this integral operator, I can see how this could lead to other zeta values. Thank you for your question.
Thank you.
Jean-Paul?
Yeah. Can you hear me?
Yes.
Okay. Thank you very much for this nice talk. I mean, it's fascinating, all these products. So my question is probably a little bit too general, so to say. So you sort of open the way to billions of formulas, of fantastic products. And do you think there is some hope for having a sort of, I don't know, a sort of unifying way of getting all of them, or at least many of them, in one way, if I may say?
I see what you mean in terms of the question you provided, and this seems to relate to, or this seems to touch upon what I was describing earlier when I referred to this research topic that I described with this bullet point. When I referred to how we could mimic or build upon the given techniques concerning the 2A Moore sequence and the period doubling sequence using automatic sequences much more generally. So what do I mean by much more generally? I tried to be careful with my language, and I suggested we could use infinite families of automatic sequences satisfying certain constraints or certain conditions. So I don't have any concrete or immediate or definitive response based on what you characterized as a general question, but it's indicative of an area that I'm very interested in. How can we classify as much as possible in a meaningful way infinite products that admit closed forms and that involve automatic sequences in the exponent, and a full exploration of these classification problems is beyond the scope of this presentation, but it's a fascinating area for me.
Yeah, thank you very much. It's also fascinating I think, for all of us.
Well,
Thank you.
I'm sorry if I didn't respond to you in a very direct way. I could I could approach your problem using, say, specific families of automatic sequences, but it's somewhat difficult to to put into plain language.
Sure,
I
sure.
mean,
I mean,
plain verbal language.
yeah, actually, you did respond by using the word, which was classification. So, I mean,
Ah, yes.
absolutely. Thank you.
Are there any other questions? So I was just wondering, do these product formulas give you any sort of fast algorithm for computing the binary expansion of these constants?
Good question. I have not considered applications in the area of numerical analysis or when it comes to when it comes to computational efficiency in the manner that you have indicated. That's a very interesting question. I have found that the infinite products typically are very difficult to compute or verify numerically, which raises the question. This leads towards questions as to number theoretic applications. So perhaps with a sufficiently fast converging series, this could give light toward the irrationality measure, or if we obtain an infinite product of algebraic expressions, could this point us toward transcendence properties? I have not considered these matters in much detail, but I think it would be valuable to consider the problem of constructing faster converging products with an aim toward concrete applications in numerical analysis or efficiency of algorithms.
Thank you very much. Are there any other questions? If not, thank you. Thank you, John, for your talk.
Oh, you're